Okay. The last session we talked about potential electrode material, especially those based on activated carbon and carbonaceous materials like CNTs, templated carbons, and fullerenes. And one of the most promising carbonaceous materials that have emerged recently is graphene. And the topic of the session today will focus on graphene as an emerging potential electrode material for electrochemical supercapacitors. But in the beginning, I would like to give a brief introduction. What is graphene? Go a little bit back into the history and talk about the discovery of graphene, it starting from the 1940s, continuing with its unique properties that has made graphene like the most important carbonaceous material today. Talk about the production and manufacturing methods and techniques. Discuss a little bit about the potential applications that the world has that are being envisaged for graphene, and the commercial use of graphene as supercapacitors. What is graphene actually? Graphene is a single atomic layer honeycomb lattice of carbon atoms, as shown in the figure here. With an hexagonal crystal structure. Actually, it is a two-dimensional allotrope of sp2 carbon in the form of a planar monolayer. So what we see here is one single layer of sp2 carbon atoms that, as you can see, the unique property of those is the fact that they come as a monolayer that can be actually a very large one. It can be ranging from several micrometers, and it is a two-dimensional, the largest two-dimensional allotropic form of carbon atoms in the whole in the nature. So actually the origin of graphene comes from graphite. Graphite is the most common carbonaceous material, you know, also being being also introduced in pencils and etc. So graphene actually is one single layer of graphite, and it can be also envisaged as a carbon nanotube that has been cut and one sheet of graphene rolled into a cylindrical form can form a carbon nanotube, and we are talking about, or it can also be the essential form of fullerenes, which are also known as zero-dimensional C60 carbonaceous materials. So actually we are talking about a two-dimensional crystalline allotrope of carbon, and its unique properties come from the fact that it comes as a single layer packed in a hexagonal lattice with a carbon-carbon distance of 0.142 nanometers. Going back to the history, actually graphene theory was first explored in the 1940s by Wallace, but actually it emerged as a very potential material from the Nobel Prize in Physics at 2008, given to André Geim and Konstantin Nozelov from the University of Manchester in the United Kingdom, that produced graphene by using a mechanical exfoliation method. Actually, it is called the Scotch tape method. What they did, they just exfoliated single layers of graphite with a Scotch tape, and then they transferred those layers to a silicon substrate. In this way, they attained very high quality graphene monolayers, and actually this is a very simple way to attain graphene, as we will discuss further on the fabrication methods of graphene production. going a little bit into the properties, graphene actually owes its unique properties to the band structure, to the electronic band structure. What I would like to talk about now is the electronic structure of graphene. Correlate this structure to the conductivity of graphene layers, which are known to be actually very high conductive, especially in the in-plane direction, but relatively low. They exhibit relatively low conductivity in the z-axis, and the electronic band structure of graphene actually is correlated also to the thermal conductivity of graphene, and these unique properties will result into different applications that we'll discuss further. Okay, as we discussed at 2010, Nozelov and et al. Discovered that a high-quality graphene monolayer can be obtained from the Scotch tap method and the mechanical exfoliation of graphite single layers from a simple graphite structure. Actually, when they studied these layers that they obtained by this very simple technique, they found that these sheets exhibit a very strong ambipolar electric field effect with a carrier concentration ranging from 10 to 13 per square centimeter. It's a very large carrier concentration, and a room temperature mobility of 10,000 square centimeter per watt per second. So what we are talking about a very unique electronic behavior that was attained, which is totally different from those observed in the graphite. The direct observation of isolated graphene monolayers that year actually sparked exponentially the growing interest on this material, especially the initial interest came from the solid-state physicists, and after that it became more and more interesting for material scientists, for chemists, and also for engineers to look into more details into the properties of this unique material. Actually, when we look at the graphene properties, what it is very unique is, first of all, the structure. We are talking about two-dimensional crystalline structure, actually with low defects. Usually, there are some defects in the edges or in the corners of the monolayer, but overall, since we are talking about a very large surface area monolayer of this hexagonal sp2 carbon atoms configuration, in overall this layer exhibits a very low defect density. Actually, and the second unique property is that graphene films have no dangling bonds. What does it mean? It means that when we talk about the electronic conductivity in the in-plane surface, then it will exhibit a very high electronic conductivity in the in-plane axis. On the other hand, when we talk about the vertical conductivity, then there graphene will have a limited vertical conductivity, and this is something that it has to be taken under consideration, especially when we talk about graphene applications in those let's say three-dimensional structures or architectures that actually require electronic conductivity also in the vertical axis. Regarding the bond, the graphene bonds are the graphene bond structure, or it consists of carbon atoms which are bonded into pi bonds. In terms of the surface area, the graphene sheets are impermeable and hydrophobic. So we are talking about a very high surface area angle, as it can be shown graphically in this picture over here, when you can see that the wetting angle of the liquid on the surface area of the illustrated hexagonal two-dimensional graphene layer here is almost vertical, is almost 90 degrees. It is a very strong material. We are talking about strength being 10 times more than the other allotropic form of carbon, diamond, and also it's the tensile strength of one monolayer of graphene is 100 times higher than those of stainless steel, which serves today as the main structural material. Graphene has also very unique optical properties. It can serve as a conducting transparent monolayer sheet, and it can serve to replace the current ITO material used in most of the displays and screens. For example, as you can see here illustrated in this figure, one sheet of graphene has a very good transparency and also a very good conductivity, especially, as I said before, in the planar axis. And this is actually exhibited in this picture over here, when you can see that one sheet of graphene actually has good transparency. You can read the graphene frontiers. These are the manufacturers of that graphene sheet that is being demonstrated over here. When we talk about the optical properties of graphene, which you can see that are of great interest, actually they result from the strong pi-to-pi optical transitions in graphene and the large domain sizes, giving rise to a novel nonlinear optical properties with high laser damage threshold energy. We are talking about broadband absorption coefficients ranging from the UV up to the near infrared spectra, and sub-picoseconds up to microseconds responses by structural modifications. So graphene is not only a unique material for electronic applications, but it can be a very unique material for optical applications as well. On the other hand, you can see that one sheet of graphene is very flexible. So it gives rise to graphene application in the whole world of flexible electronics. And actually this is envisaged to be the most promising market sector for graphene, flexible electronics. In terms of the surface area properties, we are talking about a very lightweight material with a high surface area. For example, a 20-meter diameter sphere of graphene would weigh only 1 gram. So taking under our consideration this kind of properties, as you can recall from the previous lessons that we discussed about, the high surface area and the overall combined with the lightweight enables graphene to be a very promising material for electrode applications within electrochemical energy storage devices, either batteries or electrodes for supercapacitors, as we will discuss later on. In order to summarize the unique properties, I've prepared this kind of transparency that actually emphasizes the most specific properties of graphene. We are starting with the excellent electrical conductivity in plane in the XY axis, reaching up to 106 selenium per centimeter. We are talking about very high theoretic specific surface area, reaching above 2,620 square gram per meter, and these are values actually taken from the literature, from different researchers, especially located in US academia. As you can remember, for activated carbons, the surface area ranges somewhere from 700 square meter per gram up to 2,000 square meter per gram. So graphene has even higher surface area, 2,600 square meter per gram. And if we compare graphene surface area with carbon nanotube surface area, then it has a surface area higher by a factor of 5, because carbon nanotubes, as you might recall, exhibit 400, 500 square meter per gram. This gives rise to exceptional intrinsic double layer capacitance. We are talking about approximately 21 microfarad per square centimeter, and a very high theoretical capacitance reaching above 550 farad per gram. Just to compare, in moderated to high quality activated carbons, we talk about 130, 150 farad per gram. So we are talking here about a factor of 5 again, multiplying the specific capacitance of graphene material. In addition, it has a very high mechanical strength. We talked about the very strong chemical bonds pi bonds between carbon atoms, and we talked about graphene strength being higher by 2 orders of magnitude in comparison to stainless steel, which is the most common structural material today. Or we talked about strength of 10 times more than the diamond. So it is a very strong material. It has a high chemical stability, and it has a very high thermal conductivity. So there is quite a broad range of potential applications that this emerging material can be applied to. Production methods. Actually, we talked about these unique properties of graphene, and whereas the multiple functionalities of graphene have been extensively explored, and you have today in most of the notable universities groups that are focused on graphene research. On the other hand, manufacturing techniques are quite in the beginning stage, so they are quite in the infancy stage of this material. And today you can actually divide the manufacturing methods into main ones. One is a mechanical, one uses a mechanical approach, and the other one uses a chemical approach. So when we talk about the mechanical approach, we talk about the mechanical exfoliation, or the mechanically splitting layers of graphite into fabrication of monolayers of graphene. So the most notable method is the Scotch tape method, and and this is actually the method that Game and Nosoleil used in order to attain the graphene layers that gave them their Nobel Prize. And we are talking about a delicate plus time-consuming technique, but it can produce up to 1 square millimeter sheets. Very large sheets actually can be attained from this method. Actually, the highest quality of graphene monolayers today have been attained from this Scotch tape method, especially when the source has been a high quality graphite. This is a very, let's say, necessary condition in order to attain high quality graphene. You have to have a high quality graphite source. So this technique can be the technique of choice, but actually it is suitable for basic research for foreseeable future. It is possible to automate this process by using, for example, ultrasonic cleavage. Actually, the ultrasonic cleavage is the one that splits the graphite layers and leads to stable suspensions of sub-micrometer graphene crystallites. This method can allow the production of graphene on an upscaled industrial scale. Another method actually that is being used today most commonly in the industry is the chemical production. The chemical production focuses on three main fabrication techniques. The first one is the epitaxial growth of graphene on a silicon carbide substrate or on a metal substrate by using a chemical vapor deposition technique. The second chemical method is the soluble fragments of graphene being prepared through chemical modification of graphite, especially graphite reduction. Actually, this is in comparison to the CVD methods, which are very costly techniques, and also the surface area of the surface size of the graphene sheets is limited to the wafer, for example. The chemical modification of graphite via reduction method is actually more cost effective than CVD manufacturing or fabrication technique. Another way is to cut open those cylindrical CNTs, those cylindrical carbon nanotubes, using chemical methods, for example, using potassium permanganate and sulfur acidic treatment in order just to open wide the carbon nanotubes and to attain monolayers of graphene. So this graph over here actually tries to summarize schematically the quality versus the price, and the price actually is taken for mass production. And you can see here, for example, that the highest quality of graphene is attained via mechanical exfoliation, that Scotch tape technique that I talked about before, and usually it is done in the research institutions, in the academia, or for producing a prototype in order to show a proof of concept. A more industrial technique that also results into high quality graphene is the chemical vapor deposition technique, and actually this is a very well-known technique that serves today the industry in the area of coatings, in the area of transparent conductive layers, electronics, photonics. So we are talking about the usual chemical vapor deposition that we know from the microelectronic industrial sector. Graphene growth, epitaxial growth on silicon carbide or metal substrates can be used for electronics or RF transistors. Actually, we are talking about a moderate quality, but it is enough for this kind of applications. The liquid phase exfoliation, actually, which is the less expensive technique, is also used for composites or inks, and this is the most known method today used for graphene production for electrodes in those energy storage devices. Another method that is used more for nanoelectronics is related to the molecular assembly. This is actually a very exotic method, and again, it serves only the university groups, and it is not industrial upscale, and it is not today an industrial upscale method. What I wanted to show here is some commercial graphene examples of CVD graphene sheets attained on a nickel substrate. We are talking about samples that can be purchased today via the internet in the graphene supermarket, for example. We are talking about samples in the range of 10 millimeter to 10 millimeters, so 1 square centimeter surface area of CVD graphene films on nickel. These optical and SEM images of those films show, for example, the microstructure of graphene, and you can see that the CVD actually is done on a silicon wafer, which of course has on top of it a silicon oxide layer. On top of it, it has the substrate, the nickel deposited, and the thin layer of graphene on top of it. We are talking about, in this way, the layer thickness in these samples, for example, was not the ideal monolayer of 0.14 nanometer thickness, but there were actually three monolayers of graphene attached to one another on top of the nickel substrate. So we are talking about a thickness of approximately 0.45 nanometer of graphene layer. Another well-known company that provides commercial graphene samples or examples is the Extron company. This actually is taken from their presentation given on the Graphene conference and in the end of 2014 in Santa Clara, USA. And we are talking, what they show here is their BM product line that produces monolayer graphene on what they call a BM Pro 4 per 6-inch area. So the typical process is to produce graphene on a copper foil, usually via CVD method. We are talking about a very high temperature process that occurs at 900 centigrades, and it's a methane-based growth process. So in order it's a usual CVD methane-based growth process. Actually, what you can obtain from this apparatus and from this way of producing, you can have a large square area of graphene sheets. You can transfer them manually from one substrate to another. The process can be heated up to the process temperature, which, as I said, it is 900 centigrades, and actually the quality of graphene depends on the parameters such as the time, for example, that the growth time and the pressure, of course, and the temperature anneal. We are talking here about a high temperature anneal, and after the graphene growth, the apparatus is cooled down to room temperature, and then the samples are obtained on a copper foil and can be manually transferred to other substrates if necessary. So when we talk about the graphene properties, we talked about the two-dimensional structure. We talk about its high conductivity, its high strength, its lightweight, its impermeability or its inert nature, the flexibility that makes it very potential for flexible electronics, the transparency combined with the high conductivity, the low defects, that suggest a very wide and broad range of potential applications. So the impact of graphene has moved well beyond the field of beyond field effect transistors, and has actually expanded rapidly into many other applications, especially in electronics. For example, with intraband and free carrier transitions in the microwave and terahertz regimes, it is expected that graphene, for example, will improve the performance of conventional electronic and photonic devices, especially those that operate in the terahertz frequency range. So we talk about graphene exhibiting a very unique electronic properties. Another unique property of graphene is that it exhibits a very long spin diffusion lengths, and we are talking about 100 micrometer range that are much longer than those used in or observed in conventional semiconductors or conventional metals. So the combination of that expected long spin lifetime with the high electron velocity that I mentioned just some slides before, being in the range of thousands of square centimeter per volt per second. So the combination of these two reveal the potential of graphene for spintronics, for example, and also, as you can see here, you can see that the area of electronics and spintronics and photonic devices, such as laser components and photodetectors, is the most emerging and also most emerging and potential applications that can be applied to graphene today. Another thing that I would like to talk about is about the metrology or the metrological investigations of the quantum Hall effect, for example, in graphene, have demonstrated that a quantum resistance standard is more robust in graphene than in gallium arsenide, for example, based semiconductors, and one can benefit from the recent helium-free cryogenic techniques that can be developed, and graphene can be applied into them. So this gives rise to the application of graphene in the whole area of microelectronics, and also this comes together with the fabrication and manufacturing techniques, which are very similar to those used in the microelectronics. So this is also an emerging market sector for graphene applications. So compared to other nanomaterials, one atom thick graphene sheet with a two-dimensional planar geometry can enhance electron transport for more effective devices for energy applications. So this gives rise to the application of graphene in the whole field of energy conversion as well as energy storage. So we talk about application of graphene in solar cells, for example. We talk about application of graphenes as potential electrode material for both batteries or supercapacitors. We talk about application of graphene in the catalytic layers of fuel cells, let's say in those GDLs, or usually made of activated carbon, very conductive black activated carbon. Graphene can potentially be used also in that sector due to its high electronic conductivity and due to its high surface area. So the field of energy storage and conversion is also an emerging field for graphene applications. We did not talk about the biological area or the biological field, but graphene actually, there is a lot of research in trying to implement graphene for biosensing and for bioengineering. With regards to this kind of biological realm, graphene is a very biocompatible material and could interface with biology for applications relating to the electronics, so biosensing and bioimaging applications in enzyme biosensors or DNA biosensors or immunosensors and cell imaging have all been explored not only in the laboratories but also in some small startups, especially in the US. So in terms of the market and size and timing, which is a very important issue when we talk about the implementation of novel and new materials in the industry and in the market. What we have here What we have here in the x-axis is the potential market size, and in the y-axis and on the x-axis we have the market readiness in terms of time. So we are talking about the current 2014, 2015, and what will be in 2020. So what we have for today market, we are talking about graphene for research, mainly for R&D, for research and development. We are talking about graphene being ready for some TEM, transition electron microscope grids, and there are some antimicrobial coatings and smart glasses. But the most, let's say, the booming time of graphene application predicted by this market size and timing diagram here will be somewhere in 2020, where graphene will be more effectively implemented in a variety of industrial devices, such as electronic thermal management devices, membranes for filtrations, electrode materials in supercapacitors or batteries, barrier films in displays or touchscreen due to the high conductivity and high transparency of graphene monolayers, applications, electronic applications in the terahertz regime or range, frequency range. This is somewhere even in the later future. We are talking about silicon replacement. This is something that actually could open a new area of applications in semiconductors, and of course there are some technical and band gap hurdles that have to be overcome, but also this is something that is being envisioned for graphene in the next decades. The application timeline versus the properties, and when we talk about properties, as we said, we talk about mechanical, thermal, optical, electronic, barrier and multifunctional properties. The arrow here actually shows the stage of the research, and we are talking about the common stages of the well-known research pipeline, starting with the early stage research, trying to show or to prove a conceptual proof of concept, going further with a prototype, a commercial engineering prototype, trying to enter the market with that prototype, and in the end of the day trying to make some commercial revenue. So where are we today, and how this pipeline is going, how graphene implementation in the market is going to be affected by this pipeline, is going to be applied in this timeline. Here, today we are in the early stage research, trying to show a proof of concept or the conceptual research, and here there are a variety of applications, starting from anti-corrosion coatings, those electronic packaging, graphene cables and wires with improved conductivity, tires, automotive fuel tanks are being envisioned to be produced by graphene due to the high strength and to the inert nature of graphene and being resistant to corrosion. Electrostatic paintings or membranes for water purification and filtration, photosensors, logic and memory devices, biosensors, DNA sequencing sensors, structural electronics. All these applications are today in their early stage of or conceptual research. What has actually moved forward into a commercial prototype are examples of graphene-based electrodes for supercapacitors or batteries. There are some examples of MEI shielding based on graphene, some plastic bags and bottles, and some thermal conductive composites. In a further stage of a market entry, we have lubricants actually consisting graphene-based structures or particles. We have conductive inks. We have RFID tags or antennas, smart packaging, and flexible connectors. And of course, the material itself, in terms of upscale and manufacturing and industrialization, has become more commercial in terms of the novelty of R&D in preparation of the material itself. So, existing applications of graphene are in this tennis rackets, for example, where they, due to the high strength and high impact strength capability of graphene, in those flexible battery straps, and here I'm giving actually commercial existing applications that you can go and buy today in the market there. So this is a flexible battery strap of Vorbeck. We are talking about RFID antennas of Vorbeck as well. Inks or fluids, drill fluids of graphene nanochem. It's also high-performing bike tires. This Italian firm Directa Plus Vittoria actually presented lately this high-performance bike tires that are made of graphene, and of course we are talking about some kind of niche applications up to date, but still there are some graphene-based examples out there in the market, and this is very encouraging. Medium-term applications, as we said, supercapacitor electrodes or battery electrodes. We are talking about ESD mats or flexible TCFs. Regarding longer term applications, there is the whole biological kingdom of DNA sequencing or biosensors. There are the area of transistors and microelectronics. We are talking about tires, membranes, water filtration, for example, having nanoporous graphene, trying to purify or to make selective differentiation between fresh water and salt water. We are talking about anti-corrosion coatings containing graphene, and then reinforced polymers or lightning protection. So there are plenty of applications where graphene can find itself implemented within. The latest examples that I wanted to show here are taken from some giant companies, and one of these examples is the Samsung graphene flexible displays. Samsung actually patented a screen that does not require a source of life, and this actually is made of graphene. The approach is based on reflection of ambient light by a thin film layer on top of electrodes, and this thin layer actually is graphene, and it exhibits changing optical properties under the influence of applied electric field. In addition to that, color filters would be deposited on the top of the graphene film layer in order to generate the RGB with a protective layer on top of it all. And this is the Samsung graphene flexible display shown in 2014, so it's a very latest example. And actually Samsung is the leading industrial company which owns the largest portion of patents on graphene related research, and it puts a lot of efforts in terms of internal research and outsourcing for graphene R&D and implementation and industrial implementation. Another example actually are the 3D graphene printed batteries, 3D printed graphene batteries. As I said, graphene could be used to could be incorporated within a battery during the building process, leading to electronics with built-in power sources. This is something very new and very novel, emerging lately, and the ability to be built in via the building process of the overall device opens a new door of applications. For example, Volvo demonstrated in 2013 a Volvo car with 3D printed graphene battery. The car's body panels serve, for example, as a battery. And what is specific in this S80 sedan test vehicle is that Volvo demonstrated the special body panels that are largely made of carbon fiber that act as batteries. So the body panel batteries can charge faster than conventional cells and reduce the weight compared to the standard design of steel body panels, and have a separate battery pack. So, for example, what they show here schematically in this picture is the latest nanomaterials made of extremely thin and strong carbon fibers being replacing the car's steel body panels, and can be used in the car's roof and car's doors and bonnet and floor. And these panels also double and can serve as the car battery itself. So what you have here is, due to the lightweight material and to its strengthness, you have a 15% reduction of the car's weight. And there is potential even for cutting more weight into the further design improvement. The expected range of driving range of this vehicle is 130 kilometers. Take in mind that in 2013 this was quite a pioneering range, when the EV vehicles, usual vehicles, could not drive. The upper limit was, and in a flat terrain, was 100 kilometers. So having a 2013 an expected range of 130 kilometers, it is attained only via the implementation of graphene and carbon fibers in the car body panels. So in terms of the electricity, the body panels are discharged as the car's electric motor is used, and the material can be recharged by, first of all, harnessing the energy generated when the car brakes. So we are talking about the regenerating the braking energy. If you remember in the first lessons that we talk about the application or supercapacitor applications in the automotive sector, actually what makes supercapacitor a very attractive device for this kind of application is the ability to recuperate or regenerate the energy via braking, when braking. So here it is done actually in situ by using this kind of graphene-based panel bodies and structural parts. Another way that the material can be charged is by plugging into the main electrical grid and being recharged very fast. So what we have here, we have the electrodes, we have the carbon fiber, the fiberglass, and the carbon fiber. So what we have all in all is like a cell consisting of two carbon fiber electrodes or graphene electrodes, and the fiberglass actually acting as the electric separator between them. So we have essentially a supercapacitor cell. Actually, this will give us the main motivation to go and talk a little bit about graphene-based supercapacitors and see how graphene can be implemented in the supercapacitors as potential electrode material.